Oh no, we are leaving the real world and diving into the world of the imaginary. What? That means we must be talking about complex numbers. So let's remember the principal square root. The principal square root of 25 is 5 because if you square 5, you get 25. Well, what about the square root of negative 25? Can you square any real number to get negative 25? What if we did try that negative 5? Well, negative 5 squared is negative 5 times negative 5, which is a positive 25. So even if we squared a negative 5, we wouldn't get negative 25. Because of this, we have the ultimate imaginary number, the square root of negative 1, which happens to be I. Okay, so let's just jump right in and start talking about a few of these things. Before we go too far though, what about the cube root of negative 27? How is this different than the square root of negative 25? Why do we know that the answer to this one is negative 3? Well, if we were to take negative 3 and cube it, we would get negative 3 times negative 3 times negative 3. Negative 3 times negative 3 is a positive 9, and 9 times negative 3 is negative 27. So you can take the cube root of a negative number and get a negative number, but you cannot take the square root of a negative number and get anything that's real. Okay, so the gist of it is, if a radical's index is even, remember this is your index, this little number, if it's even and the radicand is negative, the number underneath is negative, then you have an imaginary number. How about that square root of negative 25? Let's think back to the prison method where we write the prime factorization of this number, which is just 5 times 5, and I went ahead and split it because 5 times 5 is 25 times negative 1 is negative 25. So I went ahead and split it into the real part and the imaginary part. Well, the square root of 25, we know that these partner up and 1 makes it out. The square root of negative 1 is I. So the square root of negative 25 is actually 5i. How about the next one? We have the square root of negative 50. The prime factorization of 50 is 2 times 5 times 5. But because we have a negative here, we have the square root of negative 1 off to the side. These little guys partner up. The 2 has to stay there because he doesn't have a partner. So 1, 5 makes it out. The 2 stays underneath. And the square root of negative 1 is I. Now to write this in a form that looks a little better, we usually put the I in front of the square root. That way it doesn't look like the I is under the square root. So we would write this as 5i square root of 2. Finally, we have the square root of negative 108 x squared y cubed z. We went ahead and took out the negative, wrote the prime factorization of 108, that's 2 times 2 times 3 times 3 times 3. We have 2 x's, 3 y's, and a z. Now we need to partner these little guys up so the 2's can partner and the 3's can partner. That one's going to stay inside. These x's partner, these y's partner, and these 2 stay inside. So we have a 2 on the outside, a 3 on the outside, an x on the outside, and a y on the outside. On the inside, we still have a 3, a y, and a z. And of course, the square root of negative 1 is I. Well, let's make it look a little better. 2 times 3 times x times y is 6xy. We'll put the I in front of the square root. And we have simplified that square root into an imaginary number. That one involves all those wonderful variables as well. Complex numbers do have a standard form, and the standard form is the real part plus the imaginary part, or a plus bi. So looking at this example, we have the square root of -9. That is the square root of 9 times the square root of -1. The square root of 9 is 3, and the square root of -1 is I. So normally we would just stop there and say that that is the simplified form of that expression. However, the instructions tell us to put it in standard form, which means we need a real part plus an imaginary part. So this one doesn't really have a real part, so we just put 0. 0 plus 3i. This would represent the standard form for that complex number. When you want to perform operations on complex numbers, you simply treat the imaginary part like a variable, but then don't forget what it actually stands for. Remember, I is the square root of -1. So keep that in mind, but still work them as normal. So when you're adding them, just add the real parts. 3 plus 2 is 5. Add the imaginary parts. -4i plus 5i is a positive 1i. Make sure the answer is in standard form, so real plus imaginary. When you subtract complex numbers, just distribute the negative first, and then treat it like addition. So we have 3 plus 7i. Negative times negative is a positive. Negative times negative is a positive. Now we just add them. 3 plus 11 is 14. 7i plus 2i is 9i. Real plus imaginary. Multiplying them, we're going to pretty much distribute everything in the first parentheses to everything in the second. So 3 times -11 is -33. 3 times -2i is -6i. 7i times -11 is -77i. And 7i times -2i is -14i squared. So we're going to combine our like terms. So we have -33, -6 and -77 is a -83. Now we have this I squared over here. Let's think about that for just a second. If we have I squared, that's like saying this. So I squared would be the square root of -1 all squared. Well, when you square a square root, they cancel each other out. So I squared is just -1. Ooh, that was a little bit deep, wasn't it? So I squared is -1. So that means we have -14 times -1. Negative times negative is a positive. And now we have even more like terms. We have -33 and +14. When we add those, we get a -19. So we have real plus imaginary. For division, first of all, you want to make sure the numerator and the denominator are both in standard form. And this is very important. You cannot leave a radical in the denominator. Hopefully you remember that from our pre-algebra. Remember that I is the square root of -1, so I is a radical. That means you cannot leave an I in a denominator. So we do what's called rationalizing the denominator. So let's review rationalizing the denominator from before. If we have a square root of 3 in the denominator, we need to figure out how can we partner up whatever's in there so that they can escape, right? So that just means we need another 3 under the square root. Well, whatever you do to the denominator, you have to do to the numerator, right? So that's 4 square roots of 3 over, if you multiply those, you get the square root of 9. I'll go ahead and write that down. The square root of 9 is 3. So we have gotten that radical out of the denominator. Well, how about number 2? You can do this one the same way, but if you just multiply by the square root of 8 over the square root of 8, then you will have a little bit more work to do in the end. Before we do that, let's break down this 8. That's 2 times 4. That's 2 times 2 times 2. So this is the same thing as 4 over the square root of 2 cubed. 2 times 2 times 2. Well, for those little guys to be partnered up, I need one more 2. So that these can partner up and these can partner up, right? So I only have to multiply by the square root of 2 over the square root of 2. Well, 2 cubed was 8, and 8 times 2 is 16. So we have 4 square roots of 2 over 16. 4 square roots of 2 over square root of 16 is 4. And 4 over 4 reduces to 1. So this entire expression simplified into the square root of 2. So those were supposed to be a little bit of a review for you. Now what about when there's an I in the denominator? Remember, I is the square root of -1. Well, if it's just an I can multiply by I over I. Multiply straight across. 4 times I times I is I squared. But what did we say that I squared is equal to? Remember, I is the square root of -1. So if you square both sides, I squared is equal to -1. So that's 4I over -1, which is -4I. Pretty cool, huh? Alright, so what if we have more than just an I in the denominator? More than just one term, to be more specific. We have a complex number, which has a real part plus an imaginary part. To get this I out of the denominator, you have to multiply by its conjugate. Remember, its conjugate is the same two terms, but the opposite sign. 2 plus I. So if we multiply straight across, we have 4 times 2 plus I all over 2 minus I times 2 plus I. Well, now we have even more i's in the denominator. So let's see what we can do. I'm not going to distribute the numerator just yet. It is possible it will reduce, so I want to leave it factored for a little while. Multiply out the denominator. 2 times 2 is 4. 2 times I is 2I. Negative I times 2 is negative 2I. Negative I times I is negative I squared. So we have 4 times 2 plus I. 2I minus 2I is 0. I squared is -1. So this is going to end up being 5. I can see right away that 4 and 5 won't reduce. So I'm going to go ahead and distribute my 4. We have 4 times 2 is 8, and 4 times I is 4I. All over 4 plus 1 is 5. Now remember, you're supposed to keep your real friends and your imaginary friends separated. I mean numbers. You're supposed to keep your real numbers and your imaginary numbers separate. So we separate real plus imaginary. Now it is in standard form. We're going to try just a few. I'm going to go through these kind of quickly, so if you do need to go back and review, since it's a video, you can just pause and rewind and play again. So the first one we're adding, we add the real parts. Negative 6 plus 6 is 0. I'm just going to leave it completely simplified. So I won't write a real part. I plus 3i is 4i. On the next one, we need to distribute the negative. Negative times positive is negative. Negative times positive is negative. Negative 6 plus negative 6 is negative 12. I plus negative 3i is negative 2i. Number 3, we are multiplying. Negative 6 times 6 is negative 36. Negative 6 times 3i is negative 18i. I times 6 is 6i. And I times 3i is 3i squared. Combine like terms, negative 18 plus 6 is going to be negative 12. And I squared is negative 1. Three times negative 1 is negative 3. The real parts will be negative 36 and negative 3. That's negative 39 minus 12i. Number 4, these are conjugates. 6 plus I and 6 minus I. So something really cool is going to happen. 6 times 6 is 36. 6 times negative I is negative 6i. I times 6 is 6i. And I times negative I is negative I squared. When you combine your like terms, they cancel each other out. Negative 6i plus 6i is 0. So we have 36 minus I squared is negative 1. 36 plus 1 is 37. So when you multiply complex conjugates, you get a real number. Simplify 2 over I. Remember, we can just multiply by I over I. That's 2 times I over I times I. I squared is negative 1, and 2i over negative 1 is negative 2i. On number 6, we have a complex number in the denominator. So we multiply by its conjugate. So we have 3i times 1 minus I over 1 plus I times 1 minus I. 3i times 1, 3i times negative I. 1 times 1, 1 times negative I times 1, and I times negative I. I squared is negative 1. Negative I plus I is 0. I squared is negative 1. So we have 3i, and then negative 3 times negative 1 is positive 3. So 3i plus 3. 1 plus 1 is 2. So we need to write this in standard form, which means we need to rearrange these. So we have 3 plus 3i over 2, but you have to separate your real and your imaginary. So we have 3 over 2 plus 3 over 2i. Number 7 is like number 6. There's only a slight difference, but it's not too bad. We do have a complex number in the denominator, so we multiply by its conjugate, 2 minus I over 2 minus I. That's 3 minus I times 2 minus I, all over 2 plus I times 2 minus I. Multiply 3 times 2, 3 times negative I times 2, negative I times negative I. 2 times 2 2 times I, negative I times 2, and I times negative I. We have like terms, so we have 6, negative 3, and negative 2 is negative 5. I squared is negative 1. We have 4, negative 2i plus 2i is 0. I squared is negative 1. So we have 6 plus a negative 1, that's 5, minus 5i, all over 4 minus negative 1, that's plus a positive, so that's 5. So we can separate real and imaginary. That's 5 over 5 minus 5 over 5i. Well, 5 over 5 is 1. So we have 1 minus 1i, 1 minus I. Okay, we're going to do a little bit of investigation with I, and then we'll be finished. So remember, I is the square root of negative 1. I squared is the square root of negative 1 all squared, which is just negative 1. Okay, so stay with me here. Isn't I cubed the same thing as I squared times I? This 2 plus this 1 makes that 3, right? Well, I squared is negative 1. And negative 1 times I is negative I. So I cubed is the same thing as negative I. Well, what is I to the 4th? Can we say that that is I squared times I squared? But I squared is negative 1. And negative 1 times negative 1 is positive 1. So I to the 4th power is actually a positive 1. Oh my goodness. Okay, let's keep going. I to the 5th. Let's say that that's I to the 4th times I. Well, what's I to the 4th? I to the 4th is 1. And 1 times I is just I. So wait, I to the 5th is the same thing as I. Okay, so what about I to the 6th? Can we say that's I to the 4th times I squared? But I to the 4th is 1, and I squared is negative 1. 1 times negative 1 is negative 1. So I to the 6th power is negative 1. So what about I to the 7th? Can we say that's I to the 4th times I cubed? Well, I to the 4th is 1. I cubed is negative I. 1 times negative I is negative I. Okay, finally I to the 8th. Let's say that's I to the 4th times I to the 4th. But I to the 4th is 1. So that's 1 times 1, which is 1. Do you see what's happening here? We have I, negative 1, negative I, 1. I, negative 1, negative I, 1. That pattern will continue on and on and on forever and ever. I, negative 1, negative I, 1. It just keeps repeating over and over and over forever. So why do you think I went back and started using these I to the 4ths to start with? I'm sure you're thinking that I did that because I to the 4th is 1, and that's correct. So if I can figure out how many I to the 4ths there are, that's just 1 to some power. 1 to some power is just 1 times 1 times 1 times 1 times 1. It's just 1, right? So if I can mark off all of my I to the 4ths, then whatever's left over is my answer. Let's see what that means. If I want to know what I to the 252nd power is, I want to know that's I to the 4th to what? I to the 4th to what? So take your calculator. 252 divided by 4 is 63. I to the 4th to the 63rd power. 4 times 63 actually is 252. So these two expressions mean the same thing. But I to the 4th power is 1. 1 to the 63rd power is 1 times 1 times 1 times 1 times 1, 63 times. That's just 1. So what if it doesn't divide exactly like this one did? How about I to the 133rd power? That's I to the 4th to the what? So we have 133 divided by 4. We know it's around 33. Well, what is 4 times 33? It's 132. 132, but I need 133. That means I need one more I. So this is I to the 4th to the 33rd. All this represents I to the 132nd. When you multiply it by another I, you get I to the 133rd. So all of this means the same thing as that. But I to the 4th to the 33rd is 1 to the 33rd power. 1 to the 33rd power is 1 times itself 33 times. That's just 1. 1 times I is I. So I to the 133rd power simplifies into just I. You did it.